Good evening. My name is DJ Swanefelder. My supervisor is Ruan van der Merwe, currently working at Bytefuse. And my topic is a contrastive approach to weight-space learning. Now, what exactly do I mean by a contrastive approach? Contrastive approach refers to the field of contrastive learning, where the goal is to generate or find meaningful representations of data points. Specifically, data points that are more similar to each other should be closer in this representation, and data points that are very far from each other should be pushed away. An example of this in natural language processing is modeling the semantic relationships of words using a contrastive learning approach. Now, what do I mean specifically by weight-space learning? Specifically, a weight space is simply a lost landscape without the loss. It is every single possible value and combination of values that the weights of a model can take. And so a single point in the weight space represents a full model. Because of this, weight space learning is often referred to as meta learning. There are two main branches of weight space learning: discriminative and generative. In discriminative, the goal is to predict as well as possible by only considering the model weights, the model performance, and the model properties, such as how many data points the model was trained on, how many epochs, the generalization performance. And it's surprising how much can be found by only looking at the model weights. Then in generative, the goal is to generate high-performing model weights on unseen data. So how does contrastive learning and weight-space learning, how can you combine them for my project? And so for that, first we consider three classes of the ImageNet sub data set. We first into a latent space and generate a data set embedding. We then take a ResNet 18 neural network and train it on to classify these three classes. That will have a corresponding result, which we then also embed. And then the weights themselves of the neural network is embedded using a variational autoencoder, which also encodes and decodes to reconstruct the weights as closest to original weights as possible. Now, given these three embeddings of the weights, the results, and the data set, we make use of contrastive learning to bring the points that are similar to each other closer and those that are dissimilar further apart into a shared embedding space. The point of the shared embedding space, or the benefit of having a shared embedding space, is you can generate a new unseen data set of three subsets, specify the result which you want, do a forward pass of these embeddings, find where the point in the shared embedding space is, and then reverse the process by finding the weight embedding and then decoding that. The goal is then, of course, that weight's performance will be the same as the specified performance. That's the goal. Thank you.